In this video, we will see about wake-word detection training a model. To recognize different wake words, we need to train a new TensorFlow-like model that can integrate seamlessly with our application. The process starts with ensuring input constraints, meaning the model must be trained on audio that matches the same sample and shape and format and pre-processing steps used in our system. Next, the output format should be produce a probability score for each word class. So the application can easily interpret the results. High quality training data is critical and we will typically use large data set for spoken recordings to make the model accurate. Finally, the model must be optimized for microcontrollers, balancing accuracy with efficiency. 5. Leverage TensorFlow training, transiting scripts and open datasets. We can develop a customized wake-word model and integrate it directly into our applications. Okay, next we will see about training our wake-word model. Our wake-word detection model is trained using the TensorFlow simple audio recognition script, which builds an audio recognition model much easier. The scripts come with several useful features. It can automatically download a datasets of about 20 spoken words and lets us choose a subset for the training. It also provides a pre-processing option, supports multiple model architecture and enables which is essential for running efficiently on the microcontrollers. When the script is executed, it downloads the datasets, train the model and produce a trained model file. This file is then converted into a TensorFlow Lite format for a deployment. Using Google Colab, we can easily run the script experiments with different configurations and optimize the model for real world performance. And training in Google Colab. Google Colab gives a powerful cloud-based computing resources for training machine learning models. It comes pre-confirmed with essential tools and best part it's completely free. That steps to train our wake-word model is Colab or straightforward. First, we open the TensorFlow repository notebook and click run in Google Colab. Then we configure the training parameters based on our target wake-word. Next, we install any necessary dependencies for audio processing and model training. As the training runs, we can monitor progress using TensorBoard, which shows accuracy and loss curves in a real time. Finally, we execute the training script, build the model and convert into a TensorFlow Lite format for deployment on microcontrollers. Okay, let's see the enabling GPU training in Colab. Training deep learning models on a CPU can take hours because processing large datasets is computationally expensive. A GPU or graphics processing unit can dramatically speed this up by handling many operations in parallel. GPU are especially effective for deep learning tasks like images and audio processing, while a parallel computations are common. In practice, training on a GPU is often 5 to 10 times faster than a CPU. For example, in Google Colab, training time can drop from 3 to 4 hours down to just 1 to 2 hours. Enabling GPU in Colab is simple. Open the runtime menu, select change runtime type, choose GPU as the hardware accelerator and click save to apply. Next, we will see the configuring training in Colab. In Google Colab, we configure the training scripts using a command line flags, which let us define important parameters such as the list of words to classify the numbers of training steps and the learning rate. A key variables here is wanted words, which specify the exact commands our model should recognize. For example, setting it to on off means the model will be trained to detect only those two words. The datasets provide several categories of words, common commands like yes, no, up, down, left, right, on, off, stop, and go. Digits from a 0 to 9. And the random words such as bed, cat, dog, happy, tree, on, wow. Any words outside that list will be automatically classified as unknown. Next, we will see about defining training steps and learning rate. In this training, Wake-Word model is done in stages, each with a different learning rate. For example, we can train for 50,000 steps at a learning rate of 0.001, which allows the fast adjustment to earlier one. Then we will switch to 3000 steps at a smaller learning rate of 0.0001. It will which fines tunes the model for accuracy. In total, that gives us 80,000 training steps. The learning rate is important. A high rate speed up convergence, but the risk overshooting that best values, while a low rate is lower but generally produce better accuracy. Before running training, we also need to install the dependency. This includes installing a supported versions of TensorFlow and cloning the TensorFlow GitHub repository to access the official tuning script. Using TensorBoard for the monitoring, the TensorFlow provides the real-time insights to process the display, graphics of the loss and accuracy, statics about model performance, training progress for overtime. To load a TensorBoard in Colab. Once the training begins, the TensorBoard will be visualized the model learning process. In the figure, a screenshot of the TensorBoard after training is completed. Okay, next we will go to being training. To begin training the Wake-Word detection model, it's following command in your Google Colab notebook. Understanding command arguments. First one, wanted words. It specifies the words to train. Example, yes or no. Silence percentage. It defines how much silent audio is included. Third, unknown percentage. Says the percentage of words classified as unknown. Quantize. Enable mod quantize for the microcontroller efficiency. How many training steps? Number of training steps. Learning rate. Learning rate for training adjustments. Train directory is the directory to save the trained model. In the screenshot of TensorBoard at the beginning of the training. Users, how do I monitor the training process? You can use the TensorBoard as visualization tool for tracking the training performance. TensorBoard provides the two graphics key points. One, accuracy graph. It shows the percentage correctly. Cross-entropy graph. It will be measure the model predictions or from the correct labels. The training process takes around 2 hours to complete. While running, the logs won't be printed continuously, but the TensorBoard will updating the graphs. To ensure the seeing the updated, click the rightmost button under each graph to adjust the scale to fit. In this figure, we can see the accuracy and cross-entropy graphs. In this section explains how the cross-entropy is used to measure the loss. In the TensorBoard, key points. Cross-entropy loss. It's measure the predicted values are from the actual category. Second one, graph. Its jagged lines represent the performance on training dataset. Second one, straight lines represent the performance of validation dataset. It's the third one, validation dataset. It's evaluated less frequently. So there are fewer data points in the graph. Adjusting a TensorBoard view to better visualize training progress. First one, adjust scale. Second one, enlarge graph. Click the rightmost button under each graph to fix the latest data. Enlarge graph. Click the button next to graph for bigger view. There is a viewing model input. In the TensorBoard's images tab display the spectrogram which shows how input audio is converted into a format that model can learn from. In this dashboard, we are see the data micro image and data spectrogram image. Next we will see about waiting for the training to complete. Training will be take 1 to 2 hours, and during this time we can monitor the progress using TensorBoard. Understanding training graphs. The matrix as a training progresses making the graphs appear fuzzy. This is the normal since training data varies, but it can make a trend hard to interpret. Using smoothing in TensorBoard. In TensorFlow provides the smoothing feature to make the trends clearer. Steps to applying smoothing. Locate the smoothing slider in TensorBoard. Adjust its increasing smoothing, and the original data remains visible to lighter color while the smoothed trend is clear. Preventing Colab from disconnecting. As the Google Colab automatically shuts idle session for a free up resources. Since the training takes time, we must keep the runtime active. Manually interact with the notebook every off zone after. Run a small scripts that prevent Colab from the idling. We can see in the figures, we can adjust the smoothing sliders. And the training graphs with increasing smoothing, we can see the accuracy and cross entropy. Okay, next we'll see the keeping Colab in next video.